Hi, in this video we are going to talk about the k nearest neighbors classifier. So let's get started. What is a nearest neighbor classifier? A nearest neighbor classifiers can classify and label examples by assigning them to class of the most similar labeled examples. So it is very simple, but on the other hand it is extremely powerful and widely used in practice. The KNN, as they usually call it, this k nearest neighbor, KNN, is well suited for classification tasks where the relationship between the features are very complex or hard to understand. What are these features? Features, for example, in the last video we saw linear regression, for example, the size of the house or the size of the bedrooms or the number of bedrooms, for example. These are the features. And if the relationship between these features are very complex and hard to understand, that's where we can use KNN very efficiently. So we have a training data set, the examples that are classified into several categories, and we have, for example, a new example with the same number of features as the training data, and the KNN identifies k elements in the training dataset that are the nearest in similarity, and the unlabeled test example is assigned the class of the majority of the k nearest neighbors. So for example, we have features such as ingredients, sweetness, crunchiness, and we would like to have a guess according to the type. So for example, the apple have a sweetness 10, the crunchiness 9, and we classify it as a fruit. The bacon has a sweetness 1, crunchiness 4, and the type is protein. These are just fake data, by the way. I don't know whether bacon is a protein or not, whatever, and of course I don't know whether the sweetness and crunchiness parameters are correct, whatever. It is just for demonstration purposes. And for example, we have the tomato, and the tomato has the same number of features as we have discussed, the sweetness, the crunchiness, the ingredients, and we want to have a guess about the type. So what can we do? First of all, we create a plot. On the x-axis there's the sweetness, on the y-axis there's the crunchiness, and we get a plot something like this. The cheese, the fish, and the bacon has a very low sweetness parameter and a very low crunchiness parameter. But for example, vegetables has a high crunchiness parameter, but they're not so sweet. Fruits are sweet in the main, so we can classify it something like this. The green dots are the proteins, the blue dots are the fruits, and the yellow dots are the vegetables. And for example, we have this tomato with a certain crunchiness parameter and a certain sweetness parameter, and we want to classify it whether it's a fruit, it's a vegetable, or it's a protein. So what can we do? We need a so-called distance function in order to be able to classify the tomato, and the Euclidean distance would be great. If you are familiar with math, this is the equation, how we calculate the Euclidean distance. We have a point x, we have a point y, we just have to calculate the square root of the x1 minus y1, we square it, plus x2 minus y2, and we square it, and we go as far as the number of features in our examples. So for example, we have these ingredients, we have the sweetness parameters and we have the crunchiness parameters, and we want to calculate the Euclidean distance between the tomato and the carrot. So we just have to use our equation. We have to calculate the square root, and 6 minus 7, because the sweetness of tomato is 6, and the sweetness of carrot is 7, so that's why we have to write 6 minus 7 and we have to square it. The second parameter is the crunchiness. So the crunchiness parameter of tomato is 4, the crunchiness parameter of carrot is 10, so that's why we have to calculate 4 minus 10 and the square. And if you calculate it, it is going to yield us 6.0 0.083. So this is the distance. And we calculate it for all the other types of food. I mean, for the carrot, for the apple, for the bacon. It's very important that we have to calculate the distance between the tomato and the other vegetables or fruits, because we want to classify the tomato. So that's why the tomato is the first parameter of this distance function, always. And if the k is 1, which means that we consider the smallest distance, so the first item that's the nearest to the tomato. And because both of them, for bacon and banana, has the smallest value, the 5, we don't know it for certain. If the k is equal to 2, we consider the two smallest distances, bacon and banana. So we have 50-50% that tomato is a fruit or a protein, because bacon was classified as a protein, banana was classified as a fruit. If the k equals to 3, it means that we consider the 3 smallest distances, the 3 items that lies closest to the one we want to classify, so the tomato. It is the bacon, the banana, and the cheese. The bacon is a protein, the banana is a fruit, and the cheese is a protein. So we have 2 protein and 1 fruit. So tomato appears to be a protein. So we have to choose an appropriate k, because deciding how many neighbors to use for k and n determines how well the model will generalize the future data. If k is very, very small, it's going to be a noisy data, or an outliers have a huge impact on our classifier. It is called underfitting. If the k is very large, it is the overfitting problem. We have the tendency to predict the majority class regardless of which neighbors are nearest. And it's very important that this k and n is a lazy learning. What does it mean? A lazy learner doesn't learn anything. We just store the training data, we just store the sweetness and the crunchiness parameters, but we don't make any training. That's why the training is very fast, because there is no training at all, but the prediction is rather slow. As you may recall, for example, linear regression, we have to fit the parameters. We have to find the beta 0 and beta 1 in order to predict the linear line to be able to make future predictions. Here, we don't have to make any training operation. We just store the data. So we do not build a model. As far as linear regression was concerned, we build a linear model. For logistic regression, for example, we use the sigmoid function. We have to find the parameters for the sigmoid function. If we want to make a classifier, for example, not a classifier but a clustering algorithm, the k means clustering, we have to build a model that according to what we are going to make predictions. Here in KNN, we do not build a model. So this is a so-called non-parametric learning. No parameters are to be learned about the data. What can be these parameters? As I said earlier, for example, linear regression, we have to learn the beta 0 and beta 1 parameters. These are the parameters we are after. Here, we have no parameters because we do not build a model. It's very important. And the applications, of course. We have the optical character recognition or facial recognition, such as for images or videos. We have recommender systems, for example, whether a person will enjoy a movie or not. We can use the KNN very, very efficiently. Or, for example, identifying patterns in genetic data. So it's a very, very powerful classification or classifier, although we do not build a model. So the training is very fast, but making prediction may take long time periods. So that's all about KNN. Thanks for watching.